We introduce a novel method for probabilistic human mesh recovery in 3D scenes from egocentric views. With the rapid development of AR, VR applications, it is crucial for head-mounted devices to understand human behaviors from the egocentric view. And an essential component is to estimate the 3D bodies of our social partners. However, due to the close social distances, the egocentric images usually exhibit severe body truncations, posing great challenges for such task. Empowered by the recent advances of 3D scanning technologies with commodity sensors and the rapid progress of visual localization and mapping of AR, VR glasses, a 3D scan of the scene can be easily obtained, which can provide strong cues to infer the unobserved body parts. Given an egocentric image and the 3D environment, our goal is to generate the human mesh in plausible interactions with the scene, with visible body parts aligned with the image, and diverse samplings for unobserved body parts. Most of existing works for human mesh recovery are deterministic and ignore the diverse nature of missing body parts. The probabilistic methods typically do not consider the 3D scene information. To address these issues, we propose a novel scene condition diffusion model with a per-joint visibility-aware graph convolution denoiser. The diffusion sampling is further guided by a collision score to resolve human scene interpenetrations. A scene conditioning module encodes the input scene point cloud into a scene feature and predicts the global body translation gamma. The input egocentric image is encoded by the image conditioning module with a CNN backbone. However, the encoded global image feature cannot balance between the accuracy for visible body parts and diversity for invisible body parts. To achieve better per-body part control, we additionally exploit the per-joint visibility information. At each time step t, conditioned on the scene feature, the image feature and the joint visibility mask, the diffusion denoiser takes the noisy body pose theta t and predicts the clean pose theta 0. We propose a per-joint visibility-aware graph convolution network as the diffusion denoiser, for better per-body part control. For each body joint, the pose denoising is conditioned with the image feature for visible joints, while for invisible joints the image conditioning is masked out. The denoiser is further conditioned on the scene feature and other features. Given the human kinematic tree, we adopt a graph convolution network to incorporate interjoint dependencies and regress the clean body pose. Additionally, a shape estimator takes the scene and image features to predict the body shape beta. Given the denoised body pose, estimated body translation and shape, the full body mesh is regressed, in plausible interactions with the 3D scene, and consistent with the image observation. Apart from the scene conditions for the denoiser, the diffusion sampling is further guided by a collision score to resolve human scene interpenetrations. In the standard diffusion sampling process, at each denoising step t, the denoiser predicts the clean body pose, which is noised back to theta t-1 by sampling from a Gaussian distribution. The sampled results still exhibit human scene collisions. To solve this issue, we propose to use a human scene collision score to guide the sampling process. By calculating the gradient of the collision score with respect to body pose, we sample theta t-1 with an additional correction term to reduce the collisions in the next denoising step. This sampling strategy significantly enhances the human scene interaction plausibility. Compared with the baseline methods, the proposed model can generate human meshes in natural and realistic interactions with the 3D environment. Meanwhile, diverse poses can be sampled for invisible body parts, with visible body parts aligned with the image. In summary, we introduce a novel scene condition diffusion model for human mesh recovery from the egocentric image given the 3D scene geometry. By efficiently leveraging the scene conditions and joint visibility, we achieve per-body part control and realistic human scene interactions. The collision score guidance during the diffusion sampling further improves the physical plausibility. For more qualitative results, please refer to the appendix. Thank you for watching.